this is the expression for expression for the frequency at which we get the maximum phase. So let us do an example. Okay, let us essentially take some values for the parameters involved in the lead compensator. So you see that in the lead compensator there are 3 parameters which have to be figured out. It is Kc, alpha and capital T, right. So those are the 3 parameters involved in the control transfer function. So let's say we consider Kc to be 1, okay, we consider alpha to be, let us say 0.1 and T to be equal to 1, okay. So let us plot the Bode diagram of this controller transfer function, okay, C of s. Okay, so the exact Bode diagram I will leave it to your homework, but the construction process, because by now we are familiar with how to construct Bode diagrams. So, but I am just going to give you the answer and also discuss some interesting observations from that, right. So, with these values, please recall that the controller transfer function of a lead compensator is Kc alpha times Ts plus 1 divided by alpha Ts plus 1. If we substitute these values, we are going to get 0.1 times T is also 1. So, I will get S plus 1 divided by 0.1 S plus 1, right. So, this can be rewritten as 0.1 3 factors and then S plus 1, then 1 divided by 0.1 times S plus 1, right. So, those are the 3 factors that are involved in this particular transfer function. So, now if I want to plot the log magnitude plot, right, for the Bode diagram. So, let us do that, right. So, let us plot the log magnitude plot. So, we can immediately observe that the magnitude of C of j omega, if I plot it in decibels, so the 2 corner frequencies are 1 and 10, right. So, that is something which we can immediately observe, right. Those are the 2 corner frequencies, and we can immediately observe that the Bode diagram, okay, is going to look something like this. Okay, I am drawing the final Bode diagram, of course only the asymptotes. So, we are going to have a contribution of minus 20 due to the factor 0.1, okay, till the first corner frequency of 1. Then we are going to have a straight line with a slope of plus 20 decibels per decade between the 2 corner frequencies. So, as a result I will go from minus 20 decibels to 0 decibels as far as the log magnitude is concerned. Then after that I will settle down at 0 decibels, because the factor 1 by 0.1 S plus 1 will come into play, right. So, that is going to be the log magnitude curve for this particular transfer function, right. So, once again, you know, like plotting the 3 individual log magnitude curves and adding them is left to as an homework assignment, but it is pretty straightforward to see that this will be the final asymptotic log magnitude plot, okay. That is what I am drawing. I am only drawing the asymptotes, not the actual magnitude plot, right. So, one could immediately observe the following, okay. So, we observe the following from the log magnitude plot. So, what do we observe? We immediately observe that this particular lead compensator is going to essentially attenuate or decrease the magnitude of the low frequency components, right, because we can immediately observe that the low frequency components of the signal are going to be attenuated by the lead compensator, right. So, that is something we can immediately observe, right, the low frequencies are attenuated here. So, consequently the magnitude of the open loop transfer functions, please note that the open loop transfer function is C of s times P of s, right, because we have unity feedback. In general the open loop transfer function is going to be G of s times H of s. here h of s is 1 and g of s is c of s times p of s, right. So, the open loop transfer function at low frequencies is decreased, okay. So, that is something which happens. So, this would immediately imply that this can potentially lead to increase in steady state error, right, because please remember, you know, like if the low frequency values are reduced, the value of KPE, KVE and all essentially are affected, right. So, they go down. So, as a result, you know, like the steady state errors may increase, right, due to what to say this particular aspect, okay, this particular characteristics of the lead compensator. Of course, this depends on the type of the system, whether we have type 0, type 1, type 2 and so on, right, which we have already looked at, right. Depending on the type of the system, the steady state errors corresponding to certain inputs may increase, okay, with this particular aspect. Now, if I want to ensure that, you know, like that is not the case, then what should I do? What I should do is that I should push up this magnitude plot, let us say up by 20 decibels, right, for example, alright, considering this particular example. Suppose if I shift this entire log magnitude curve by 20 decibels by multiplying by a factor of 10 as far as the controller is concerned, what will happen is that the low frequency components will now have a magnitude of 0 decibels as far as the controller transfer function is concerned. So, consequently, the values of Kp, Kve, Kae are going to be not affected, right. So, the steady state error characteristics will still be retained as far as the original system is concerned. But what would happen? We immediately see that the high frequency components will now be magnified, right, they will be amplified because I have to shift the entire Bode plot up by 20 decibels. So, consequently, the high frequency components get shifted out by also 20 decibels, right, in this example. So, consequently, the magnitude of the high frequency components will increase, right. So, that is something which can be observed from here. So, we can immediately note that the second observation is that if we increase Kc, right, to address the first point, then note that the high frequency components would be amplified, okay. That is a flip side of having what to say, shifting this factor, right. So, if we essentially increase the value of Kc to address this problem, we see that the high frequency components are also what to say essentially amplified, right. So, that is something which is an observation. Now, if I plot the, before plotting the phase plot, right. So, in this example note that omega m is going to be equal to square root of 1 divided by square root of alpha t, which is essentially square root of 10 radians per second, right. And sine of phi m is essentially 1 minus alpha divided by 1 plus alpha, which is essentially 0.9 divided by 1.1. This implies that phi m is essentially around 54.9 degrees, okay. So, that is the maximum phase which is added by this particular lead compensator, okay, the example that we are considered. So, if I plot the phase plot for this particular example, right. So, this is also something which I leave it to you as a homework exercise. So, but I am just going to plot the final plot. So, if you plot the phase plot of C of j omega in degrees, what we are going to get is the following. So, 1, this is 10, okay. So, on a logarithmic scale, square root of 10, which is a geometric mean, is going to be in between, in the middle of 1 and 10, right. and let us say we start from 0 degrees and then let us say like we reach a peak. So, if you plot the phase plot, what is going to happen is that it is going to look something like this. It is going to start from very low values, right, and then as frequency increases, okay, it will reach a maximum at square root of 10, and then it will start to decrease. Okay, ultimately it will go to 0. So, at square root of 10, whatever is the maximum value, that we have calculated to be 54.9 degrees. Okay, so that is the maximum phase for this particular lead compensator. Okay. So, to summarize, a lead compensator is typically used when the given system or plant does not have a sufficient phase margin to begin with. So, what we intend to do is essentially to add a positive phase to the system to ensure that we increase the stability margins, right. But what was the trade-off here? Like we immediately saw that the magnitude characteristics is like a high pass filter. So, essentially what happens is that like it amplifies high frequency noise if we are not very careful, right. But there is a trade-off once again, right. In order to not amplify the high frequency noise, we keep the low frequency components at a lower magnitude, then the steady state error characteristics are going to be affected, right. The steady state errors may increase. So, in order to avoid that, if I push the magnitude plot up, the high frequency components are going to get amplified, right. So, there is a trade-off here, but the good thing is it will essentially give us a positive phase lead, which will increase the phase margin of the system. Okay. So, this is the theory behind lead compensator. In the next class, we will essentially do a problem where we will start with a given system, and we will see how to design a lead compensator for a given set of performance specification requirements, right. We will go through all the steps and then like calculate the values of Kc, alpha and T to meet the given performance requirements. Okay. So, that is all with today's class. We will learn an example of lead compensation in the next class. Thank you.